All right. You guys now know everything that you were supposed to know about electrostatics. We are now going to start talking about circuits. So in this intro video, I'm going to be talking about what's really kind of happening inside of a circuit, and then I'll define three of the big terms you need to know. You'll need to know voltage, current, and resistance. But first, let's dive into what happens in a circuit. You guys have probably seen circuits before or played with them at some point. If you have a battery, you can hook up some kind of lights to it, and depending on how you set it up, you can get different brightnesses and you can light up different number of bulbs and so on. So I have on the screen right here a circuit that I set up involving three different lights where two of them are on the same wire, kind of like one after the other, and then there's another one on like kind of a separate little circuit. But if we dove into these and we looked at what was really happening, inside of each of these wires are electrons that are being pushed by the battery. But it's important for us to realize that the battery is not creating electrons. It is pushing electrons through it via chemical reactions, but those electrons have to come back to it. So when this battery starts to flow, uh, when we first connect it and things, we have all of the electrons already in there. They're already attached to the various copper nuclei or whatever the wire is made out of, and they're just kind of chilling. But when I hook it up to the battery starts causing them to move through there. But they all have to move together. It's like in a traffic jam. If one of them stops, they all have to stop. So when I connect them, it doesn't start moving here and then like as time passes go further and further and further. What really happens is that all of a sudden everything starts moving at once. And they all have to move at the same time because in order for the electricity to keep flowing, I have to have charges coming back into my battery to replace the ones that it's pushing out the top end. And along the other side of my circuit, the same thing's happening. The electrons are getting pushed through there, or actually the positive charges. I'm drawing this as positive charges because I don't care what they are. In reality, again, they are electrons, but it doesn't matter at all. And in fact, on the AP Physics formula sheet, it says that they're talking about positive charges, even though that's wrong. They say we talk about conventional currents as being positive charges because electricians just don't care about electrons. Uh, so uh, so that's the idea of circuits, is that they have these charges inside of them that get pushed around by the battery, but they're not created by the battery. They're just moved by it. And whatever's happening in to one charge kind of has to be happening to everybody. If one of them's moving fast, they're all moving fast. The same way that if we are all charges driving on the freeway, if one of us is driving fast, we better all be driving fast. And if one of us gets in a car accident, we don't all get in a car accident, but everybody else has to stop. So if you imagine that it was kind of like a closed racetrack, if one person stops, even the people ahead of him have to stop if it was like totally packed. So hopefully that all made sense just now. So let's start defining some terms. The first one that we're going to talk about is voltage, which can also be called electric potential, or voltage drop. Now, those terms aren't actually synonymous. When you take Physics 2, you will learn what the difference is between those different terms. But for Physics 1, they are basically interchangeable. And if you see any of them, I want you to just think we're asking a question about the variable V, capital V, not lowercase. So with this voltage V, that is the energy per charge that we have. So the units, if we zoomed in on them, would look something like, like joules per coulomb. It's how much energy each charge has. But writing joules per coulomb for every time is kind of time consuming. So we tend to just write it with the official unit of voltage, the volt. So 1 volt is 1 joule per coulomb. And as charges go through the circuit, they're going to start turning that energy, that electrical energy that they were each given by the battery, into other forms of energy. So passing through this first light bulb, there is an energy transformation from electrical potential into light and thermal energy and things like that. And so basically what happens is when I come out of the battery, I had some charge, but then I'm going to drop down when I get to my first battery, my first light, we'll call that light A. And then moving through the next part of the wire right here, my voltage will stay exactly the same. And then when I move through my next light bulb, I will transform some more of my energy into light and heat. And then by the time I get to the bottom of the battery, I have 0 energy. And the battery is going to pump the energy back into those electrons and send them out to go do their job again. If I go along the other branch, I go along the branch that has light bulb C on it, it's going to look slightly different because what's going to be happening here is it's starting at the same spot because both of these had, I don't know, 6 volts or whatever. But as I go through this way, this battery is actually going to use up all of it, or not battery, sorry, this light bulb is going to use all of it all up at once. And what the effect of that is actually light bulb C, because it's using more energy, will likely be quite a bit brighter or hotter or something like that. Okay, so that's voltage. And if we're measuring voltage, the tool that is used is called a voltmeter. And when we use a voltmeter, we always have to wire it up on either side of the object we care about. So if you're trying to find the voltage of C, it would be 6 volts, and we would just connect the voltmeter on either side. If I want to find out the voltage of my battery, I'd hook up to either side of my battery. And again, I would find out that my battery has a voltage of 6 volts. And if I wanted to find the voltage of A, I'd hook it up there. I'm getting a little lazy with my drawing here. And it would probably be, I don't know, something like 3 volts. And then my other one would be using up the other 3 volts. It doesn't have to be 3 volts. One of them could be 1 volt and the other one could be 5 volts. But they definitely have to use up all of it as they go through there. So that's some of the important voltage stuff. If you talk about voltage, if you have a problem with voltage, it's typically a problem involving conservation of energy, because voltage is all about electrical energy being given by the battery and carried by the charges and then being transformed in the resistors into some other thing. So the energy is conserved, it's just transferred between forms or carried from location to location by those charges. Okay, next thing to talk about is current. When we talk about current, we're now no longer talking about the energy of the particles, we're talking about how fast they're moving past a particular spot. So when we talk about that, the units for that would be how many coulombs are passing per second. And instead of writing coulombs per second, we really write that as the official unit is amps. The variable for it is I, so like make sure you're keeping track of the different variables and units here. So current, when we use it in equations, we represent it with the letter I, but the units of it are amps. So we would have 1 amp, 2 amp, 3 amp, and so forth. Let's see. You can really think of current as being that like analogy that I just shared earlier about like cars on a racetrack, or you could think about it like a closed circuit with like a water pump attached to it. The battery is the pump, and that's creating the current. But it's only creating the force that's pushing it. We also have resistance in each resistor, and each one of those light bulbs is going to be fighting the current a little bit and slowing it down. So if I add more resistors, I'm likely to decrease the current unless I give it more paths, and then some more can get through along the different paths. Let's see. When I'm measuring current, I'm going to measure it with ammeters. So you measure it with an ammeter. But an ammeter has to be hooked up very differently from a voltmeter. When you hook up an ammeter, you have to actually break the circuit. So if I want to put my ammeter in, I now got rid of the wire that used to exist there, and I put my ammeter directly in there. That's different than the voltmeter. The voltmeter was outside the circuit and connected across 2 points. The ammeter has to join the circuit and be part of what's happening. That's what lets it measure the amount of current that's passing through it, because it has to kind of like, not literally, but it has to be counting the electrons that are going past in order to give us an accurate value. The voltmeter just wants to measure the energy at one spot and the energy at another spot and tell you the difference. So that's why it's outside the circuit. The ammeter has to be part of the circuit so it can tell what's happening going through it. What else do I need to say on current? Problems that involve current are really going to be questions involving conservation of charge, because the idea there is that we can't have electrons just or charges just disappearing. So anywhere that we have current, if it splits or comes back together, the total amount of charge going through our circuit always has to be the same. Finally, our last thing to discuss. If I was putting an ammeter in here and I had an ammeter at each location, I would probably find that I had something like 6 amps. I'm sorry, wait, right? Yeah, 6 amps along this side, 3 amps here, 3 amps here, 3 amps here, 6 amps here, but I would have 9 amps going through my battery, because as those charges are passing through the battery, some of them are going to go one way and some of them are going to go the other way. But I have to be pushing the same number of charges through the battery in order to then send them along each particular branch. An important thing, final thing on current, is that current prefers the path of least resistance. It won't all go along that path, but the majority of it will. So you can see actually that it's preferring the left-hand side that has that one light bulb, because there's less resistance on that side. So more of the charges are going that way than are going on the side that have 2 light bulbs. And we'll talk about why that is a little bit more later, but the idea that it prefers to go on that path of least resistance is an important qualitative tool that you can use. Finally, let's talk about resistance. Resistance is how much any object is going to be fighting the flow of electricity through it. Resistance is really caused as those those charges are being forced to surrender their electrical potential, and it's being transformed into other things. So resistors come in many different forms. They could be light bulbs, they could be heaters, they could be vacuum cleaners. That's literally every single resistor I can think of right now. That's probably the only 3 that exist. Um, Maybe there's more. I don't know. I'm just a science teacher. That's the idea of resistors. And resistors are measured in the units. We use the variable R to represent them, but the units for them is the ohm. And we write the ohm with the variable capital omega. So that is, one more time, like officially it looks like this, but you'll see Mr. Terrell mostly just draws it like pretty lazy like that. So we can have all kinds of different resistors going on in our circuits. If you're trying to find the specific resistance of a wire or resistor or something, there is an equation if you know all of the variables for the resistor. If you know its resistivity, its length, and cross-sectional area, you can find the resistance directly. Otherwise, you won't be doing it unless they give you specifically length and area information that we'll talk about in a later video. You will never be asked to directly measure the resistance. Instead, you will somehow measure the current and the voltage and use that to figure out what the resistance must be. Or in a later video, we'll learn how to add resistances of different resistors together to find what's called the equivalent resistance. So for example, when I set this problem up in my head, each one of these were 1 ohm resistors, and the equivalent resistance of these two together is a 2 ohm resistor. Like if we took them out and we just wanted to know how much resistance they were providing together, we wanted to replace them with a single light bulb instead of 2, we would replace them with a 2 ohm light bulb instead of the 2 1 ohm light bulbs, and it would have the same effect. The equivalent resistance of my whole circuit is actually, oops, that was ugly, but is actually 1.5 ohms. And we'll learn about why we didn't just add that other one in there later. It looks like I averaged it, but I didn't do that either. Okay. Finally, on resistance, we will always assume, unless otherwise stated, that wires and batteries have no resistance. That's not strictly speaking true, but it's close enough to being true that for the problems that you guys are going to be asked to do, it will greatly simplify them so that you can actually start practicing the basic skills before you take Physics 2, where we will not make that assumption as often. So that's all of the introductory stuff on circuits. It's a lot of stuff, but you guys are going to be good at this. And if you're not good at it, I'll be shocked.